At two-way tables, it's a chi-square inference test, and what we're looking for is independence. Well, for either of the chi-square tests, it's independence, homogeneity, and goodness of fit. Typically, for a chi-square two-way test, we're looking for independence. All right, we're looking to see if two variables are related to each other in some way. So I had this example here. It talks about gender versus political affiliation to see if there's a relationship. All right, the whole solution is there, so you can read through it. But when we talk about whether or not there's a relationship, we're talking about independence. Independence shows no relationship between two variables. Dependence shows that there is some relationship between the two variables. This is the first hypothesis test where we're actually just going to state the null and alternative hypotheses in words rather than using symbolic notation. So as long as you get across the idea of no relationship for the null, some relationship for the alternative, and that no relationship corresponds to, oops, that's not a marker, no relationship corresponds to independence, and some relationship corresponds to dependence. We'll do this in more detail on a separate page. All right, but that's really the idea. As long as you can word your null and alternative hypotheses in a way to address those two ideas, then you'll have it. The directions say to construct a table of expected values, and they give you these lovely formulas. So what's happening is, in a two-way table, you're given the observed outcomes. All right, so the observed outcomes are what actually happened. We need to compute the expected outcomes, or expected values, which is what should have happened based off of the row and column totals. All right, so when you know the totals for the rows and the columns, then you're able to determine what should be an outcome for each cell. All you do is you take the row total, multiply it by the column total, and divide it by the grand total. All right, sounds easy because it is, because we're not actually going to do that. We're going to let the calculator do it. All right. So we'll compute our chi-square test statistic based off of the observed values that they're giving us and the expected values that we're going to determine. All right. And so all this stuff here is wonderful, but it's all going to be embedded in the computation. Same idea here. You see the calculation of the test statistic is pretty crazy. There's 1, 2, 3, 4, 5, 6 separate computations. What we're going to do is what we did yesterday, and again, if you weren't here, you'll pick up on this, but we're going to do 1, 2, skip a few right to the end. All right, we're just going to set it up and then let the calculator do all the work for us. P-value the calculator is going to give us. We just care about the notation. We'll get to that, and then the conclusion. All right, so some summary values here, statements here, and we'll go right into an example. I have one that was in the packet, but I like to do a different example for each class so you have solutions to both. All right. So this is on the separate page. A sport preference poll yielded the following data for students at a local high school. Fair warning. I don't know if it's really a warning, but it's just like just so you know, I totally made up this example earlier today. Never tried it, so I have no idea if it's going to work. But it'll be a fun exploration. All right, so use a 0.05 significance level test to claim that test the claim to determine if sport preference and class are independent. All right, so like you might think people come into high school and they're like, oh yeah, it's all about basketball and football, and then as they go through their high school experience, maybe they pick up on some other sports. Maybe volleyball gets more popular, lacrosse, things like that, or maybe it goes the other way around. Like people have like a lot of different preferences, but then as they get older, they settle on just one or two. Who knows? That's what we're going to try to find out. All right, so our null hypothesis, I'm going to use a thicker marker. All right, so our null hypothesis, they specifically use the word independent, so we'll do that. We'll use that. So sport preference, independent from class. You could also say class and sport preference are independent, however you want to word it. The second sentence, or the second hypothesis, is really just going to be exactly what you wrote for the first one. Just drop the in. All right. Oh, and I suppose change the from to an on. All right, so they're independent from each other, or they're dependent on each other. All right, so we're gonna see. 5% on the alpha. I'm gonna draw a chi-square distribution. All right, it's gonna be skewed to the right, heavily skewed to the right. All right, all chi-square distributions are skewed to the right. And only right-tailed, which is nice. It kind of trims out a lot of the stuff that we were concerned with in other hypothesis tests. The tail on the right corresponds with the alpha value, 0.05. The center of the hump, that's our degrees of freedom. We'll get to that in a minute. Critical value is going to be a chi-square. And unfortunately, that's not something the calculator is going to give us. But fortunately, it's something we could very easily get off of the tables that the College Board provides for the exam. All right, so it's kind of double-edged sword, I guess. The one thing is, I mean, you're always going to be provided with the tables, so it's going to be there. It's just a question of, like, when you're doing problems on your own, if you don't have the tables available, you're like, how do I get this number? Well, the answer is to get the tables. Right, so at this point, I mean, you could do it digitally, but I mentioned this a couple classes ago, I do have plenty of hard copies. If you want to start looking at it, I can give you a copy to keep. Right, so degrees of freedom, the definition, or the formula, we know the definition for the most part, number of rows minus 1 times number of columns minus 1. Right, it's basically you're applying a degree of freedom to each of the variables. All right, so we have 3 rows, so 3 minus 1. And we have a lot of columns. Let's see, 3, 4, 5, 6, 7 columns, so 7 minus 1. So 2 times 6, so 12 degrees of freedom. So that goes in the center of the hump there. All right. Oh, yeah, you're right. I put the answer in the question. I don't know why I do that. Like a mental block. 18 degrees of freedom. Oh, change it down here too. So it's a kind of a thing that I've been trying to overcome for like my entire teaching career. Like if a question says take the square root of 16, I'll write down the square root of 4 like on the board, because I'm like, I got the answer already and it just overpowers the question. I don't know, it's just something mental on my end, of course. All right, so we go to the chi-square table in the AP Statistics formula sheet or formula packet. We got all this stuff here. Talked about a little bit of it. You go down to the very end. The very last one is a chi-square. I have it highlighted from another problem, but basically you're just matching the alpha value, which is 0.05 in this case anyway. So my highlighting actually works, with your degrees of freedom, which I believe I said was 18. And we're just looking for where those two intersect. So it intersects here at 28.87. That's an alpha of 0.05 with 18 degrees of freedom. All right, so 28.87 is the magic number. All right, so now the test statistic. All right, the test statistic chi-square is equal to the sum of the observed minus the expected, O minus E squared, divided by E. Now, we don't have any E. We have plenty of O, We don't have any E. These guys aren't here. All right. Just locking in the attendance. All right, so we're going to start putting the information in the calculator because not only do I need the expected values, I need some help with these computations because I'm going to have to run, let's see, 7 times 4, yeah, so 28 separate computations if I had to do this by hand, which would be terrible, right? Instead, we're going to do it in the calculator in the inference menu. All right, so I'm just going to kind of bring it right back to the beginning. You go into chi-square, under inference tests, you go to chi-square. The first one is the goodness of fit test. I mean, they're actually both goodness of fit. It's just NumWorks decided to name this one goodness of fit. In chi-squares, we're always testing to see if the distribution of observed values is a good fit for the population, right? Distribution. So it's the second one we want. I just kind of look at it like the first one is for one-way tables, the second one's for two-way tables. 1, 2, first, second. That kind of makes sense to me. So you go to the second one, and bottom line is if you go into one and it doesn't seem to have a place for you to put the information that's consistent with what's on the document, then you go to the other one, right? So group 1, I have 20. When you hit enter, it goes down the line, so it'll overwrite whatever's there. All right. You see it has group E listed there just in case I want to put a value in there, but it's grayed out, so it's not being considered, which is good. 25, 32, 50, 41, 30, 27, 15, 25. Group 4. Group 4 is lacrosse, so 75, 76. 88, 82. Wrestling, 61, 63, 68, and 70. 90, 92, 97, and 98. And my last group, 20, 28, 30, and another 28. All right. Alpha value is 0.05. Here's hoping I typed in everything correctly. We'll find out, I guess, at some point. Next. Now it gives us all of the expected values. Right? So that computation of taking the row total, multiplying by the column total, and dividing by the grand total is something we don't really need to worry about. Right? But what we do have to do, and this is not fun, is you got to make a note of what all the expected values are. Right? So you didn't have to compute them, but you still got to write them down. All right, so what I do is I just kind of tuck them in the table. So 24.43, 27.4, 27.86, 28.31, and I'll just throw a highlighter on it at some point. 37.55, 38.17, 38.8. Scrolling down, scrolling. Nope. There we go. 21.94, 24.61, 25.02, 25.43. Don't worry about the last value in any row or column because those are just the totals anyway. 72.62. And again, these are what the value should have been. Now they're estimates because they're the observed values are counts. These must be estimates things because if they were observed, they would be whole number values. All right, not the case here. 82.79, 84.15, 59.27, 66.47, 67.58, 68.68. Just got to get it down. It doesn't have to be pretty. 85.28, 95.64, 97.24, 98.83, and then at last, finally, 23.98, 26.89, 27.34, 27.79. All right, those are all of our expected values. We do that just to get credit. All right, that's really all it comes down to, because if you were doing this for real, you would do everything in the calculator. You'd have a computer display. These computations are very easy to populate in an Excel spreadsheet. Right? So there's never a circumstance in the real world where you'd have to write these numbers down except to get full credit on an assessment. Right? But what we're going to do is, like I said, we're going to do 1, 2, skip a few. So I'm going to do, again, it's observed minus expected squared over expected for each cell. So 20 minus 24.43 squared over 24.43 plus 25, I'm just going across the rows, 25 minus 33.48 squared over 33.48. So I got the 1, 2. Now I'm going to skip a few. And by a few, I mean everything except for the last one. So plus dot, 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 plus. So we have 28. Do this real quick. 28 minus 27.79 squared over 27.79. All right. Then, next, and then it gives you the chi-square value. All right, it gives you the chi-square test statistic of 28.498. All right. Now that would fall just shy of the shaded region. So actually I created a really awesome problem here. Been known to happen. So the p-value, it's always right-tailed in chi-square. And that's, honestly, that should make sense because, half of you weren't here yesterday, so you wouldn't necessarily know, but the chi-square distribution is completely non-negative. So it starts off at 0 and then extends to positive infinity. So there's never an instance where you could actually have a tail on the left-hand side. All right, so that's the rationale there. So probability that chi squared is greater than, or at least as extreme as this test statistic. All right, we don't have to do any crunching in the toolbox. Just write down the number here, 0.0549. This is one of those middle of the road p-values that would reject for some alphas but not for others. Right? So this would fail to reject for 0.01 and 0.05, but it does reject for 0.10. So this is one of those instances where the data allows you to go either way in drawing your conclusion. All right. Yeah.
How do you get the 0.0549?
Oh, I just pulled it right from the display.
Oh, I see. Yeah.
All right. So our conclusion here is that we're not going to reject the null hypothesis because it didn't make the cutoff. I mean, it's just barely shy, but we're not going to reject the null hypothesis, and we're going to ditch the alternative. The final answer, we're testing to determine if sport preference and class are independent. So there is insufficient evidence to reject the claim that sport preference and class slight rephrase of the null hypothesis, but still it gets the same idea across, are independent at the 0.05 significance level. It was 0.05, right? All right, so that is a complete example or a complete solution for the example. The only other way that we would phrase the conclusion would be that let's say it did reject, there is sufficient evidence to reject the claim. Either way, we're answering the question that's posed, right? So we don't need a follow-up because everything that we needed to address has been addressed. All right.